Hi, this is homework 4, part A1, and my name is Austin Cox. And here we're going to be deriving the differential equations for the liquid levels in 3 tanks where the um, outflow of each succeeding tank is the inflow of the next one. And here our systems are in a steady state with a inflow of 0.1 meters cubed per second to the first tank, and then it is increased to 0.15 meters cubed per second. And then the 3 tanks also have a common drainage hole area of 0.01 meters squared and a cross-sectional areas of 1/2 a meter and 2 meters for each one respectively. So to start with this problem, we know that we are in a steady state. So we know that the differential of our height with time is going to be 0, and we know that since this is in a steady state. So we are given the inflow rate, but for now I'm just going to label that as our Q in, and then this Q in is the outflow goes to here, the outflow, which is the inflow of our second tank. So you can see that we're just gonna keep like Q in, Q out, and then the Q out of this will be the Q in going to the next succeeding tank. So to begin deriving our differential equations, we know that we are going to, so as we said before, our differential with our height with respect to time is going to be 0. So that will give us our Q in at a steady state. So what we are solving for is the liquid levels in these 3 tanks. So we can denote that as H1, H2, and H3. We also have Q in going in our first tank. So this here will be Q1, Q2, and Q3. And these are representing the out and in flows of our tank 1, 2, and 3. And for our first tank, our cross-sectional area is 1 meter. So we can write that our cross-sectional area is equal to 1, and here our cross-sectional area is equal to 0.5 meters, and lastly our third tank, our cross-sectional area is equal to 2.0 meters. And again, from our problem, we are given that all 3 holes have a common drainage hole area of 0.01 meters squared. So we can rewrite that as our drainage hole area for H1, 2, and 3. And we are going to write that as 0.01 meters squared. So from there, we are going to try to find a we're going to try to form an equation to solve for the differential of volume with respect to our system and with time. So we know that the differential of volume with respect to time is equal to our rate in minus our rate out. So in this problem, we are given our rate in, and what we need to solve for is our rate out. So we can rewrite that our differential of volume with respect to time, we can rewrite that as our cross-sectional area, and that is going to be times the differential of height with respect to time. And we can set this here equal to the Qn, and that is going to be minus our drainage hole area times minus AD H1, and that is going to be times our velocity of our flow going out, which is square root of 2GH. And we get this velocity by referencing our Bernoulli's equation, and since our system is in a steady state, we can cancel out the first and last term of our Bernoulli's equation, which leaves us with just the final velocity, which is what we are looking for. And we are able to use that there. So now that we have all of our pieces laid out, we can now put them together to derive our differential equations for the liquid levels and the heights that go with each of the tanks. So using what we have here, we can write that the cross-sectional area of tank 1 times the differential of height 1 over time is going to be equal to our inflow rate, and then minus our drainage hole area of hole 1, and that is going to be multiplied by our velocity of our tank 1. So this is our first one, and I'm going to go ahead and write the expressions for tank 2 and 3. And for here, our inflow rate is going to be the outflow rate of the succeeding tank. So we can write that as such. And then this is going to be subtracted by the outflow of tank 2, and we can rewrite that as the drainage hole of 2 times the velocity of it going out of hole 2. So this is our second one, and going further we can write expressions for our third one. So we have the cross-sectional area of 3 times the differential of height of tank 3 over time is going to be equal to our inflow, which is the outflow of our previous hole or tank. So we have the drainage hole of H2 times 2GH, our velocity, and that is going to be subtracted by the drainage hole of H3 times the velocity of it going out, which is that. So here we have derived 3 differential equations, but now we are going to need to derive the expressions for our H1, H2, and H3 so that we can come up with a set of initial values so that we can go into Colaboratory and solve our differential equations with those initial values. So next we are going to be looking to come up with some expressions for our height, our H variable for our height 1, 2, and 3 of the liquid levels in the tank. So we can denote that our height is going to be equal to the inflow rate squared over our drainage hole area squared, and then that is going to be multiplied by 2 times gravity in our denominator. So this is our expression for H. So now we can go ahead and throw in our actual values for each of our individual tanks to come up with 3 expressions to use as our initial value problems in our differential equations. So we can write that H1 is going to be equal to Qn squared over our drainage hole of hole 1 squared times 2G. And then for hole, our height 2 is going to be the Qn squared, the inflow rate squared, times the drainage hole area of 2 squared times double gravity. And then again, our H3 is going to be equal to the Qn squared over the drainage hole of 3 times 2G. And we are able to come up with all of these expressions due to our system being in a steady state. We are able to cancel out some terms from our known equations, and we are able to plug and chug the rest back in to come up with these 6 expressions. So for our next step, we are going to take these 3 and these 3, and we are going to go into Google Colaboratory, and we are going to solve for the actual values of the heights that we are looking for, and we will use scipy.integrate to solve the initial value problem, and then we will plot using plotly.subplots. So this is it for A1.
Hi, this is homework 4, part A2, and today we are going to be solving the differential equations that we came up with in the previous part. We're going to be solving them numerically with scipy.integrate and solve IVP, and then we will plot those results using plotly.subplots. So going over to Colaboratory, we are going to first start by importing numpy as np. Next we are going to go from scipy.integrate import solve IVP, and next we are going to from plotly.subplots import make subplots. Shift enter. So now we have just imported and brought in all of our libraries that we are going to need to solve the differential equation with the initial values. So next we are going to be inputting our values that we know, so we can be just like defining all of our inputs. So to start, we can go ahead and say G, which is gravity, is going to be equal to 9. G is equal to 9.81, and our Qn naught value is equal to 0.1 meters cubed per second. Our Qn value is 0.15. The next things we're going to be inputting is our cross-sectional area and our drainage hole area, and we're going to be inputting those as arrays since we have 3 tanks and 3 values for each. So we can go AC for our cross-sectional area is equal to np.array, and it is going to be 1, 0.5, and 2. 1, 0.5, and 2. And that is our cross-sectional area as an array. So now we have our differential, and that is equal to NP dot array. And our three tanks have a common drainage hole area of 0.01. So we can just 0.01, 0.01, 0.01. So now that we have our drainage hole area and our cross-sectional areas listed as an array, we now need to lastly input a time to end our simulation, and we can make that 1,000 seconds. Shift enter. Next, we are going to input our height knot value, and we derived that in our previous part. So we can go h knot is going to be equal to qn knot, that is going to be squared, and then divided by our drainage hole area squared times 2 times g. So this is our h knot value. Enter. Next, we are going to define our function dh dt, and we are going to make it time as our x and h for our y value. And then we are going to define our q1, q2, and q3. q2, q3. And that is equal to our cross-sectional, or not cross-sectional, our drainage hole area times the square root of 2 times g times h, which is our velocity, and that is raised to the 0.5, because that is the square root of that. And from here, we are going to return the output of our 3 tanks, return the 3 outputs for each of the tank. So we know that the flow rate is going to be equal to the flow in minus the flow out. So here our flow in is going to be qn minus q1, and then that is going to be divided by our cross section. And we are going to make the index of that 0, so it pulls from the first value. So this is our first output, and next we are going to want to return the second tank, so it will be q1 minus q2, and then that will be divided by AC, and then pulling from our first index. So that is our drainage hole for the second tank. And lastly, for our third output, we are going to make it q2 minus q3, and that value is going to be divided by our cross-sectional area, pulling from our second index, which is our third value here. So now that we have our return statement here, we can go ahead and go shift enter. So now that we have defined our differential equation and set up the return value statements for it, we can define our height variable, and we're going to use the solve IVP function in order to solve the differential equation that we have set up and come up with values for our answer. So our function that we are going to be solving is dh dt, and the time span is going to be starting from 0, and then we will go until t end. our initial height we can input as h naught, and then we need to realize that we need to use the dense output function. It just numerically integrates a system of differential equation, and it will give us the initial value. So we can write dense output is equal to true. Shift enter. Next we are going to set up our plot that we are going to be plotting our results on. So we can go tplot is equal to np.linspace, and we're going to start at 0 for our parameters to tend, and then we can just stop at 500. Next we are going to have to unpack our height because we have 3, and we need to just unpack it so we can use each one while we are plotting our results, so that we have 3 different heights for each of the tanks. So we have h1, h2, and h3 is equal to height dot sol and then t plot. So basically what that does is gives us our height solutions and then returns it to our plot. So now that we have set up our plot and our height, 3 values for our height, we can go ahead and make our plot. So we can denote fig as fig is equal to make subplots, and then we can go fig dot add underscore scatter, so we can add our scatter plot, and we want our x value to equal our tplot variable for our time and height, and then we want our y to equal h1, and we can name this plot h1 so it shows us which height it is, the height for which tank it is. And lastly, we can give our plot a mode, and we can go lines. So now what I'm going to do from here is copy this, paste. So now that we have all 3 listed with their each h1, h2, and h3, we can go shift enter, and we can take a look at our graph that we have here. So you can see that all 3 sort of come up to the same, but you can notice that they all have 3 very distinct slopes. So our h1 will be the fastest, and then h2 is the slowest, and h3. And this makes sense because if you're looking at the cross-sectional areas of the drainage hole, it is different for each one, and you know that the last one has 2, so it will have the slowest come up on that rise. Thank you for watching homework part A.